In this video, we're going to take a look at an overview of a goodness of fit test. You can see here on the second page of the notes that we have kind of this general outline that we've seen many times before. Not much is going to change here when we do a goodness of fit test. We're still going to set up hypotheses, have a test statistic, analyze the data that we have, draw a distribution curve, calculate a p-value, and ultimately state a conclusion. Now, some of the things that are a little bit different here is that we're never going to be able to write our hypotheses with just symbols. We have to kind of write sentences, kind of like what we did in the previous video. In our hypotheses, we're always going to be claiming in H0 that the given set of percentages is actually correct, that our data conforms to those percentages. And H1 is always going to be arguing that the percentages that we were given, the percentages that are claimed, are not all correct, and our data is evidence of that. Our data doesn't conform to that. We'll see that in our test statistic, we're going to enter values into the calculator, specifically these observed and expected values, and we'll have to make note that our degrees of freedom, which we'll need in order to run the test, is always going to be the number of categories, like the number of different possible observed and expected frequency values, minus 1. We'll have a bunch of different checks that we'll go through in the next video when we run a test. And we have a nice test statistic sitting over here, and we'll come back to this formula in just a second. When we actually analyze the data, we'll see that we're only really going to need two values off the calculator when we run this chi-squared GOF test. We're going to need a chi-squared value, which is our test statistic value, and we're going to need a p-value, as we always do. Now when we draw our picture for this particular curve, we'll draw this chi-squared curve, and we'll note here that we're always going to have a right-tailed test. Part of the reason for this is because when we calculate our test statistic, we're going to be interested in doing here, you can see a subtraction between O, what we observed, and E, what we expected. So if these values are very far off, if what we observed is very different than what we expected, then this subtraction will produce a very large value. And when we add up all these values, that creates my chi-squared. So if I get a very, very large number for my chi-squared, it's an indication that my O's and E's, my observeds and expecteds, were very far apart from one another. And that would be an indication that we should reject H0 because it doesn't seem like what we observed is the same or close enough to what we expected. So because of this, we're always going to be looking at a right-tailed test. There are some ways that we can go ahead and use this formula to directly calculate chi-squared, and there are some instructions down here for how I would actually compute the p-value by using the calculator chi-squared CDF command if I need to, but we'll talk about that more in a later video. What we can see is that ultimately when we state a conclusion, we're either going to be, as always, rejecting H0 or not rejecting H0, and we'll have the same two-sentence conclusion that we've always had in previous sections. In the next video, we'll take a look at example 1 and come back to this tax preparation method question and try to run through a full test to see how this would work.